We are getting close to the end of the Geotalk season, but we still have 4 talks left for this semester. We have a talk next week by Hilke Jelsma, and then 2 weeks where I don't have a talk scheduled, so if anyone does have a talk they'd like to give, you're welcome. And then a special end of semester talk by Chris Hawksworth on Friday the 1st of June. So keep that in mind, but I will send that out in the next Geotalk advert. But today we get to introduce a new postdoc in the department, Rosalind Crossley. So we can give her a warm welcome, even though she's been here for a month or 2 already, but welcome. And Rosalind's going to speak about the subject of her PhD work, which she completed last year at Curtin University, and you can see the title over there. And before that, she completed a MSc degree from Royal Holloway University in London. So Rosalind, over to you, and thank you.
Thank you very much for coming to my talk. So I'm going to discuss the results of my PhD, which was on the cycling of redox-sensitive elements and what subducted serpentinites and hybridized rocks can tell us. So I'd like to acknowledge my co-authors, Katie Evans and Steve Reddy, who were my supervisors, and Noreen Evans, Brad McDonald, Hee-Jin Jion, and Matt Kilburn. This is an image of a field area in Alpine Corsica at Serra di Pigno, and I'll be talking about that in a bit. So why do we care what happens to redox-sensitive elements at subduction zones? Well, basically we know these elements are added at subduction zones, including iron and sulfur, but we don't know the oxidation state of these elements, and we don't know how much, sorry, let's just get laser, how much is transferred to, oh, sorry guys. How does it? Okay. No.
There we go. You got it?
Okay, so I just, okay, sorry. So we don't know how much is transferred to the subarc mantle or the deep mantle here. And the oxidation state of the subarc mantle is of particular interest, especially in economic geology, because current models of these, the genesis models for arc-related ore deposits require this mantle to be oxidized. So previous studies have focused on the bulk rock chemistry, which is great, but it homogenizes all the effects of the subduction cycle from seafloor alteration through to exhumation. However, if we look at the opaque minerals and we can constrain those to a certain stage of metamorphism, we can get a much better idea of how these elements are distributed throughout the subduction cycle. So samples were collected from Alpine Corsica. So Corsica is an island to the west of northern Italy, and the northeastern part is part of the Western Alps. So basically these rocks consist of internal continental slices and metaophiolites, which were subducted to a range of temperatures and pressures, from sub-green schist to eclogite facies. And the thing is, we don't know whether the internal continental slices and metaophiolites were placed next to each other in an ocean continent transition setting. There's quite a lot of field evidence for this, or alternatively, if they were placed next to each other during the Alpine orogeny. So samples were collected from 2 localities. So Capu Corvoli, which is up here. So those rocks are subducted to higher temperatures and pressures, and that's where we find hybridized rocks. And also at Serra di Pigno, where samples were collected near to and away from other types of rocks, including metagabbro and calc schist. So these are just field images of the different field areas. So we have serpentinites next to the Metagabbro and calc schists, and at Capu Corvoli we have hybridized rocks, show the chlorite schist next to Metagabbro. So in the first part of this talk I'm going to discuss the highly siderophile element distribution in subducted serpentinites and hybrid rocks. So just to give you a bit of background, the highly siderophile elements are hosted in phases with high concentrations of the redox sensitive elements, including sulfur and iron, and these include phases like sulfides, spinels, and metal alloys. So the stability of the highly siderophile element host during serpentinization and then subduction has major control on the release or retention of these elements in the slab. So there are some previous studies of highly siderophile elements, analyses of the concentrations of highly siderophile elements in sulfides from eclogites and blue schists, and also seafloor ultramafic rocks, but so far no one has studied what happens during subduction. So the methods, after fieldwork, scanning electron microscopy, energy dispersive spectrometry, and electron probe microanalysis was used to really characterize the mineral textures and the mineral chemistry. And this was followed by searching for tiny platinum group minerals on the TESCAN mirror and integrated mineral analyzer. So this is the TESCAN mirror here. It's a very fancy piece of equipment. And then whole rock platinum group element data was determined using nickel sulfide collection fire assay, and then using 4-acid digest and ICPMS for rhenium. And trace elements were determined by laser ablation with a resonetics resolution EPMA laser and Agilent 7700 quadrupole ICPMS. And this is an image of the lab at the John Zelace Center at Curtin University. So basically we can, because the silicate mineral assemblages are well constrained to different temperatures and pressures, we can use the relationship of the opaque minerals to these silicates to determine what stage they grew. So for example, in this image here, pentlandite is aligned with the antigerite defined foliation here. So we can say that was stable during prograde to peak metamorphism. In the middle photo is a pyrite grain which overprints the chlorite defined matrix, and using thermodynamic modeling, talc is constrained to lower pressures of up to about 1 gigapascal or 1.5 gigapascals. So we know that pyrite grain grew just before that drop in pressure associated with exhumation. And then in this example here, we have this pentlandite grain, which is aligned with this late retrogressive vein of antigerite. So that's related to fairly advanced stages of exhumation. So the results, the whole rock highly siderophile element distribution. So the data is normalized to primitive upper mantle, and so the data lies here. So we can see in general it's not much different to mantle values, and we compared the data to peridotite from the Kane fracture zone, which is from Allard et al. 2005, to the internal ligurides, which is from Luguet et al. 2004, and also to subducted rock from Blanco Quintero et al. 2011. And to assess the effect of other lithologies, we compared it to hybrid rinds from Peniston Dorland et al. 2012, and also to Zermatt Gabbro from Dale et al. 2009. So Zermatt-Sass is in another part of the Western Alps, basically. So the samples here, so in orange and yellow, we have the hybrid rocks, and in purple, purple is the serpentinite, which is away from other types of lithology, and in green we have serpentinite proximal to metagabbro, and in blue we have serpentinite proximal to calcschist. So basically we see elevated rhenium in the hybrid samples and some departure from the mantle values. In the next, we're looking at the sulfides in distal serpentinite. So basically, the colours are the same as for the whole rock data, but we're comparing it to sulfides from these studies. So we can see that in general, there's lower concentrations of the high siderophile elements compared to the pre-subduction sulfides. And we also see that there's this high ruthenium content, whereas except for this one here, the osmium and iridium are depleted in comparison. Now the sulfides in the serpentinites near to other lithologies. So in green is the serpentinite near metagabbro, and in blue is the serpentinite near the calcschist. And we see again this depletion, but enrichment in ruthenium, and we have variable palladium and platinum concentrations. And this is the data for the pyrite grains in the hybrid rocks, and we see that there's much lower concentrations in comparison to the sulfides from the serpentinites, and they're more in line with the concentrations that was seen in the Dale et al. Study, so the Zermatt-Sass, gabbro, and the gabbro eclogite. And as with the whole rock data, we have this enrichment in rhenium in the calcschist sample. So the first observation was that there's lower concentrations of highly siderophile elements in the sulfides compared to the pre-subduction sulfides. There's no change in bulk rock. So why is this? Well, it could have been that there's been an increase in the mode of sulfide phases during subduction. So then we would have had sulfur addition. This is a possibility, and in fact we see sulfides overprinting chromium-rich spinels here. But then we would expect to see a depletion in all highly siderophile elements, which we don't see. So the second possibility is that it's a formation of metal alloys during subduction. This is a possibility, but we need to see an anomaly specific to the platinum group elements, which we do for platinum. Thirdly, we could have had centimetre scale mobilization of the platinum group elements by fluids, but we didn't really see any sulfide-rich veins in the samples, so we don't think they've been mobilized extensively. Second observation is there's high ruthenium in the sulfides in all the serpentinite samples. So the question is, why is ruthenium sequestered into the nickel-rich sulfides? Well, we've already seen that it's not due to changes in the bulk ruthenium, because it's similar to that of mantle peridotite. So secondly, we could have had sulfidation of pre-existing ruthenium-rich chromites, which is a possibility because in this image here, we're seeing pentlandite overprinting these chromium-rich grains. So, but the chromite's not ruthenium-rich in the samples, but as we can see, they've been really altered and they've got this like porous texture. So, alternatively, we could have had the formation of alloys that lack ruthenium during subduction. So this is a ruthenium alloy from a unsubducted sample, so from New Caledonia, which could have destabilized to release the ruthenium, and then that goes into the sulfide. Or the ruthenium could have just stayed in the sulfide, and we could have had exsolution of osmium and iridium to form the osmium-iridium alloys. But the problem with this is we didn't observe these alloys in the samples. Thirdly, there's variable platinum in the sulfides. So this is attributed to the formation of platinum-bearing alloys because there's no change in the platinum concentration of the whole rock. So there's been no additional removal of platinum. So the first part, to sum up, highly siderophile elements are depleted in the sulfides, but not in the bulk rock. This suggests the possible early addition of sulfur, and then that's retained throughout subduction and exhumation because all sulfides show this depletion. Secondly, the alloy formation is proposed to account for sulfide ruthenium enrichment and variable platinum. And this could reflect changes in oxidation state and sulfur fugacity, which were currently poorly understood. So in the second part of this talk, I'm going to discuss the results from the isotopic analysis of sulfides in the same rocks. So just to give you a bit of background about sulfur isotopes, they can be used to constrain the source and redox state of sulfur and the processes that have occurred after sulfide crystallization. So basically, by studying sulfur isotopes in rocks that have been subducted and then obducted, we can assess the changes that the rock has gone through in terms of oxidation state. So, for example, modern seawater sulfate is around 20 per mil, and the mantle is around 0 per mil. And there's not, with the exception of these conference abstracts by Ramos et al. And Shimizu et al., there's no one's looked at the sulfur isotope compositions of the sulfides in subducted serpentinites. So in terms of the methods, so in the same way as I mentioned before, we did detailed mineral texture analysis, but after that we looked at the zonation in individual grains using electron probe microanalysis and nanosims mapping prior to in situ sulfur isotope analysis. And this was carried out on the Kamika IMS 1280 at the University of Western Australia. The in-house standards of VMSO pentlandite and Sierra pyrite were used. So the colour scheme that I'm going to use throughout this bit of the talk, in red we have sulfides that are related to prograde to peak metamorphism. In blue we have sulfides that are related to these initial stages of retrogression, and green records more advanced stages associated with exhumation. So basically, if we look at the sulfur isotope compositions of sulfides that have been subducted or records subduction, we can assess what's going on during subduction, whereas the late sulfides associated with the infiltration of fluids from the slab might tell us something about the isotopic composition of those fluids. So the results from the serpentinites, these were all pentlandite grains. So we can see that there's very heterogeneous values, and they're all high delta 34S compositions. So basically, between the prograde sulfides and the initial retrogression sulfides, we don't see much change. However, when we look at the early sulfide here, you can see that the antigerite is replacing the pentlandite grain with the late pentlandite grains, which are associated with these late, late sulfide, antigerite veins, we can see that there is a shift towards, sorry, the laser's just, oh no. There's a shift towards more heavy delta 34S values. And now the results from the hybrid rocks, so these are all pyrites, and we see that there's, sorry, I'm not going to use lasers, so there's more homogeneous values between the early and late sulfides. Should work. Okay. And finally, in the late sulfides, we see these really heterogeneous isotopic values in the hybrid rock. So this is the results from the electron probe microanalysis maps. So we're basically trying to see if there's a correlation between the cobalt and the nickel and the delta 34S values. And we can see that there's not really any correlation, with the exception of this moderate correlation between cobalt and the delta 34S in the talc schist sample. So the first observation was that there's high delta 34S values in all samples, and in comparison with data from other studies, so this is actually consistent with whole rock data from high pressure serpentinites in the Vulturium acid, which is part of the Western Alps as well, from Alta et al. And also they're all lie between the mantle and the Jurassic seawater sulfate values. So we suggest a mixed source between these two M members. And also we have this in the late retrogression sulfides, we have these heavier values. And this is consistent with data from mafic rocks in a study by Evans et al. 2014 from the Zermatt ZAS. And the second observation is that delta 34S is heterogeneous in certainly in the serpentinites, and this suggests isotopic equilibration is on limited length scales. So the system was rock buffered with respect to sulfur, which means that there's low fluid rock interaction, and also the it's consistent with low variance mineral assemblages. So that means that we have, with respect to sulfur, a number of different phases. And fluid infiltration, so obviously fluid infiltration is not extensive. Just to illustrate that, we have a conceptual model here. So here's a closed system, low variance mineral assemblage, and an open system with high variance mineral assemblages. And here we have the delta 34S values. So low values is in red, and in high values is in green. So when we have an infiltrating fluid, this completely homogenizes all the pre-existing delta 34S values. And in comparison, in the closed system, we just have local fluid flow, so we have very heterogeneous values. So, yep, that's what we're seeing. So there are exceptions to this, such as the difference between the prograde and retrograde delta 34S in serpentinite in the calc schist, which suggests the infiltration of late fluids with heavy isotopic compositions. And then in the talc schist, we're seeing those homogeneous values. So the system might have been fluid buffered on at least the scale of the pyrite grains. So the implications of this study is that the delta 34S heterogeneity of prograde and retrograde sulfides suggests sulfur is mostly only redistributed on a local scale throughout subduction. But the high delta 34S value suggests the infiltration of oxidized fluids, but in most cases, probably that occurred during seafloor alteration, and then these isotopic compositions were retained throughout subduction. And the homogeneous delta 34S values in the pyrites in the hybrid sample and the shift towards the higher delta 34S values provides some evidence of interaction with oxidized fluids in subduction zones. So conclusions of this study were that mineral scale investigations allow us to access a more complete record of changes to the distribution of redox sensitive elements throughout the subduction cycle, including exhumation, which is often all of these processes are homogenized if we just look at the bulk chemistry. And hybrid rocks record more substantial changes in iron, sulfur, and highly siderophile elements compared to their ultramafic or mafic precursors. And we really need to do further work to fully constrain the controls on the solubility or precipitation of the highly siderophile elements, particularly at high pressure. And so new high-resolution spatial analytical mapping techniques really do open up future pathways because we can see on much smaller scales the redistribution of these elements, and also even at an atom scale with the atom probe. So, and that's it. Thank you.
Thank you very much, Ross. Do we have any questions? I've got Malina, go ahead.
Yeah, to what extent do you think that for actually the whole redox budget of the downgoing slab, to what extent is it important that you have the influx of oxidizing fluids, and to what extent actually the loss of hydrogen during, for instance, serpentinization?
Okay. So you're asking what are the effects of the influx?
Well, I mean, generally we want to get the normal argument about subduction zones is that the subarc mantle is more oxidized than the normal mantle, and that has to do with subducting material that is oxidized. Now, you are talking about the ingress of oxidizing fluids into the serpentinite.
Yeah.
But of course, one of the other things that is actually happening during seafloor alteration is serpentinization.
Yeah,
and
sure.
it's very well known that that generates hydrogen, and hydrogen is lost.
Yes.
That bubbles out of the system. So that is actually an alternative way to actually oxidize the slag that is going down.
By releasing fluids from the suspension. Yes.
So do you have an idea of the relative importance of these two processes?
So basically, the fluids that may have been infiltrating the rocks were likely to have come from serpentinites which were further down the slab or other lithologies. So basically, as the rock is exhumed, it provides access to these fluids, and you can get a dysfunctional subduction zone where when you have the downgoing slab, it can be releasing fluids and at the same time you have the rock going up, so it provides access to these prograde fluids that are being released, if that answers your question.
Not quite to the extent. I was more thinking about what is happening on the seafloor to get things oxidized, to make things oxidized.
Yeah, sure. We have reduced conditions when you initially serpentinize something, but then there's different stages of serpentinization, basically, and it's not a simple process because actually, when you look at the oxygen and sulfur activities, and you look at your mineral assemblage, you see that actually at different stages you can have it basically falls in an area of a large range between the oxidized and the high sulfur activities. Sorry.
Alan.
In these different rock types, have you ever looked at, the readily oxidized sort of elements like cerium, various ferric iron, things like that? Does that have any influence on this?
Yes. So What I didn't talk about today is, so I also looked at what iron does, and what we find is in the late mineral assemblages associated with retrogression, you find these really large magnetite grains. So that suggests we either have oxidation of iron by the fluids, or we actually are seeing the fluids might carry ferric iron. So.
Okay. Do we have any further questions? All right. If not, then we'll leave it there. Roz, thank you once again.
Thank you.
I should also mention that Roz is working now as part of Chimera with Judith and several other people on the Platte Reef and several other deposits in the northern limb of the Bushveld. So hopefully in the future we'll hear some more talks about that. But thank you very much. Next week we'll hear from Hilke Jelsma about uranium-lead age dating in southern Angola with reference to the Congo craton. So we'll see you then.